Rightio. Okay, so an undergraduate degree in physics. I know I'm just a little bit more smart, but I was kind of feeling like being a little bit more suave in my approach to revision today. So and also half my laundry needs to be cleaned. I've been a bit lazy on that. So in that regard, that's why we have the shirt on today. But yeah, so what does an undergraduate degree in physics really entail? So I already recorded this video. You guys will probably never see that one because it was 45 minutes long. I thought, let me just go and start talking about my degree, and I gave a couple examples, but I gave examples for every module and it just took too long. So this one's going to be far more concise. This is just going to give a general breakdown of what modules are definitely done in a physics undergraduate degree. I'm going to break down what kind of maths is done as well. So obviously if you're going to do physics, you need to do maths, and you will do it. And these are the modules that you will cover. And that is universal for basically every single physics degree. Maybe one or two things won't be in some courses, but if they aren't, they're probably seriously lacking in my opinion. And then the last bit will just be some interesting modules that I picked to make my course more of a theoretical physics course, right? So, modules that you will definitely do in an undergraduate physics degree. I will try and have a little bit more editing going on and say, bang, that one, and that one, but probably won't happen. Again, I am lazy when it comes to editing, and also I'm busy as hell right now. So, now that I'm going to start, modules you will definitely do in physics degree. You will definitely be doing things like electromagnetism, quantum mechanics, and you will also be doing things like mechanics. So these are like mandatory across all physics degrees, and you technically don't have a physics degree, in my opinion, and universally, if you don't do these modules. So in a current physics degree, you would have quantum mechanics. That may be taught at like a first year or second year level. For me, we introduced it like ever so slightly in first year. I wish we did like a full module in first year, but I guess we needed to build up a little bit of the maths and everything, which I'll get onto in a sec. But quantum mechanics, you would start looking at things such as a particle in an infinite box, right? So this particle, in the normal world, you would think, for me, I'll be the particle in this sense, and I'm in my room. You can tell me I'm sitting in my chair right now, and that is definite. But it gets a bit interesting when I ask someone outside where I am, and they would go, okay, he could be anywhere in the room. And for example, you would have to guess, okay, he could be washing his hands at the sink, he could be, getting changed, checking his clothes and everything, or he could be at the chair or in bed, right? One of those four things. So essentially, currently I'm technically in what we call a superposition of all of them. And essentially, quantum mechanics is this whole idea of probabilities. So instead of 100% deterministically saying he is 100% here, you have this thing of saying 25% chance he's on the bed, 25% chance he's here, 25% he's getting changed, 25% he's at the sink, right? So that's quantum mechanics kind of in a little bit of a nutshell. You would then also look at this problem with the hydrogen atom, which is pretty common in all physics undergrads, I'm pretty sure, for a quantum mechanics course. And you would basically just talk about how the electrons work. Because if we just use normal mechanics, the electron would get closer and closer to the nucleus, bang, 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 and then just poof, annihilate. So we don't really want that. So why is it just staying orbiting and everything? So quantum mechanics will help solve that. Then you have electromagnetism. Electromagnetism, essentially, you take your electromagnetic force and your magnetic force. You would just start off with them being individual things, and then essentially what happens is you find out that, oh, there's actually a really nice relation between the two. Here you would use a lot of vector mechanics and everything, which will be covered in the math section. But yeah, basically, you would start off with your electric force. You would start off with your magnetic force, and then you find that there's a really nice relation between the two, and you do everything working with vectors. So at a university level of physics, you basically need to start working in three-dimensional space and everything. Like, that is pretty common. So you need to know your things like your dot product and your cross product, which you would cover if you do a further maths course. If you don't do a further maths course, don't worry, you're taught it. It's pretty intuitive and makes pretty like good sense and everything. Cross product's a little bit less intuitive, but you'll get used to it and you'll see it like 200 to 300 times probably in like week 3. So you'll be fine. And then the last thing that you'll definitely be doing is you'll be doing mechanics. So essentially when you come in, we've all done F equals MA. You've done it since GCSEs and everything. And essentially you would just start looking at forces. You would do things like SUVAT and, just accelerating. And it gets a bit more interesting at a university level. You actually look at like special relativity, so Einstein's theory of relativity. In the normal world, Galileo said if I was running at 10 meters per second, I know, Usain Bolt when I try my best, and I throw a ball at 10 meters per second, the ball is traveling relative to me just sitting here, 20 meters per second. But it gets a bit more interesting where if I was going at the speed of light, I throw a ball at 10 meters per second, you need to start considering these things called inertial frames, right? So inertial frames are, in the simplest way, any frame that's not accelerating. So it could be stationary or just any frame traveling at a constant velocity. And it gets more advanced at a master's level where you start looking at Lorentz transformations. You might actually even do it in an undergrad level. But that is basically the core things that you would do in terms of modules. You would also have things like coding, Python, C maybe. You learn to say hello world in 7 different ways, and that's all pretty nifty, but it's mainly just used for labs and everything. And then the last one is you would have your labs. So with labs, you would go and do your tests. No, it's not going to be anything groundbreaking. You're an undergraduate student, even at a master's level. I'm not going to find anything like that's going to change the world. Even Stephen Hawking didn't. So to expect me to do it, not a chance. I'm a mooch. So now onto the maths. With the maths, there are probably 5-6 things that are like fundamental that you're going to learn. You're going to learn vector calculus. So that's going to help you with your electromagnetism. You are also going to learn linear algebra. Linear algebra is going to help with the quantum mechanics and everything. So you're going to start looking at, just regular 3D space, for example. You're going to write it all in terms of vectors. Like I said, dot product, cross product. You're going to then also look at these things called matrices. If you do further maths, you'll see a matrix. If not, don't worry. It is in no obligation something that you need before coming to uni. You will once again, by week 2, probably see like 300-400 of these, right? And a matrix, let me give a simple one. You could essentially just take X and Y coordinates. So your Y, fuck me, lordy. X, Y, and a matrix will do a rotational one. You apply that to your regular vectors and it would just turn the space itself, right? So just turn the axes. Used very commonly. You'll do a lot of matrices like that. You also get matrices that stretch space and everything. I won't go into too much depth. 3 blue, 1 brown will always outshine me when it comes to explaining the math side of things. So I won't try and compete with that. I know where I stand, right? So essentially, you're going to do linear algebra, vector calculus, some Fourier transforms. Fourier transforms, very, very useful. You basically can rewrite all functions in terms of waves, like sines, cosines, exponentials, and everything. You find there's nice relation with e to the I theta, right? So once again, if you don't do further maths, you won't see complex numbers. You will learn all of that. So actually complex numbers is another maths topic that you will learn pretty quickly. And you can just rewrite all of your functions that exist, assume they're like continuous and everything. Maybe even non-continuous. I probably should know that, but I'm just going to skip over it. In terms of waves, very, very useful. You're also going to then, probably in second year, cover differential equations. So the most important thing to know in all of a physics degree, the harmonic oscillator. So, for example, let's just drop a ball, gravity acts down, kill off air resistance, because that guy is just a pain in the ass. Ball's going to bounce right back up to the height that you dropped it from, and it's just going to keep doing this, and that is just an oscillating motion. And you can model that using differential equations, and you will solve it, and you will just get your sines or cosines depending on your initial starting conditions. So you'll also go and learn a bunch of other things like how Lagrange went and solved it. You can use more advanced, the Dirac way, the Dirac function and everything, Kronecker delta and all those types of things, not the Kronecker delta, but your Dirac function, and you can then go on to solve things using Green's functions and this, that, the other. That's far more advanced. We really only touch upon it at a master's level, but that stuff is all just kind of, you might gloss over it ever so slightly. And then in terms of some other stuff, obviously you're going to learn stats. That's going to give you your employability skills, and then you can go and be a quant and make 200k a year and everything, if you care a bit more and you actually really delve a bit deeper into your stats. So that, I mean, at Oxford, Cambridge, half the people I know that are on the maths degree are just going to sell out and become quants. But me, I'm here for the love of the game, the love of physics. So will I do that? I wouldn't mind a summer internship where I got paid a little bit, but right now the case is I just want to keep doing physics and everything. So that's something that people would do as well. And you may start looking, we did in our maths class, but you would look at like some advanced mechanics, so Lagrangians and Hamiltonians. Won't get too deep into it, but essentially you would use that, and it's very important for when you get to like some of these theoretical modules that I picked in field theory. On the modules that I picked to make it a more theoretical side of things, you would actually have things like complex variables. So you would start looking at your complex space, and you can go on to solve some infinite integrals using Cauchy's theorem. Probably one of the coolest things in all of like maths, really. I mean, Cauchy is a titan. When you talk about Cauchy, he's like Cauchy. He is how do you put it? He's kind of like an Eden Hazard in terms of like maths and everything. Like you had Ronaldo and Messi, but just underneath you kind of have like this guy right there, Eden Hazard. So you got your Gauss, your Euler, pinnacle of maths, and then you get Cauchy, Riemann's, pretty nifty guys in the field, right? And he did a bunch of stuff. If you do any complex analysis, he will be there. Then you also have some field theory modules. So I did classical field theory, that's taught at an undergrad level usually, and essentially you would do that. I've kind of explained it, but if you just took a system, let's take the straight line, and we broke down into individual points, each point being a particle, and we then just can use some Fourier transforms and Fourier analysis, and then we can somehow rewrite this kind of like as a wave and everything. And that is a way that we start defining a field. If you give some degrees of freedom at certain points, and you can take it into a continuous limit. So we start off discretizing the line, and then we say as the space between them gets infinitesimally small, and we say the number of particles gets infinitely large, we can keep the line the same length, and that is how you land up at field theory. And that was my favorite module. Absolutely loved it. I would highly recommend it. It is very challenging. If you're not passionate about theoretical physics, you will have a hard time, but for me that was really good fun. And then actually two more modules that you will definitely do at an undergraduate level. You will definitely be doing nuclear, and high energy. So you'll start looking at just exponential decays and everything, very, very normal stuff you see at A level. And then you would also start looking at the particle side of things. I really enjoyed it. It was really good fun. You look at how some particles like neutrinos have different flavors and everything, and how they can change between these flavors. And it's a huge area of research that's currently going on, and it is pretty wicked. I mean, something that I look forward to kind of researching into, maybe doing a PhD in that type of stuff. Particle physics is kind of where I look to go down my route, if I do decide to go down the PhD route. And then the other module that you will definitely be doing at an undergraduate level is you will definitely be doing thermal physics. So you will not do an undergraduate degree in physics if you don't do thermal. So thermal would be stuff like pressure, volume, temperature. They're all related. We've seen it through experiments, and that's how thermal physics came to be. There was no derivation of this. We just saw that it all worked. Yes, you have your moles. We just set moles equal to 1 in my module. I'm sure some will care about a bit more, probably the chemists, but I couldn't care less about chemistry. Not my gig. Sorry to my brother. But yeah, essentially, you start off with that. Gets a bit more advanced, you start defining entropy, which is, you have your Clauser's form, which very impressive that a guy could go and do this ages ago and everything, and it worked very well. But then later on came Boltzmann, and he very much was able to define a far better idea of what entropy is. I say a far better one, not the exact one, because currently we don't know what entropy really is. So that is basically an undergraduate degree in physics. You have your core modules like quantum mechanics, electromagnetism, thermal, nuclear, and mechanics. Those are givens. You have your maths, which is something that you will definitely be doing. I love the math side of things. Unfortunately, I needed to pick some theoretical modules to keep the maths going. I wish they did more in third year. Complex variables, extremely useful, and field theory, just absolutely wicked. If you're someone that wants to do more astrophysics, that's the stuff that you'll pick. But me personally, I could not care less about how bright a star is, however far away. I could not care less about if there is a planet that is 16,000 light years away that is inhabitable. Wicked. We're never going to get there. So keep at it. But for me, that is not my issue. I think cosmology is a bit more interesting, but once again, not something that I'm looking to go into. But in terms of astrophysics, just not my passion. If someone wants to know more about that, I'm really not the guy. I can't help out too much. But yeah, that is basically your breakdown of an undergraduate degree in physics. I hope I sold it to you. If not, sorry about that. I mean, yeah, now that everyone knows what it is, just also know physics very, very long. Like, you know, maybe my friends watching this video can kind of go, yeah, maybe that's why Alex didn't come out too much and everything. So he was busy crunching down all these problem sheets. So for all your modules, you'll probably get problem sheets like some of them that I'm doing now. I got a QFT one in front of me. So that is all the stuff that you're going to be doing. You're going to get set some homeworks to do. You're going to do all your modules, but the homeworks really help you to go through some examples and everything. Sometimes they're graded, sometimes they're not, but it just is the best way, in my opinion. Doing questions is the best way to understand all of this stuff, and in my opinion, it's actually a very beautiful thing to go and understand. So I would say go and do a degree in physics. If you care about being more thorough, go and do math. If you could not care less, go and enjoy doing psychology and law or whatever it is. Maybe you want to speak to the Latinos, go and do Spanish, bro. So that is a breakdown of physics. I hope you enjoyed it. Hoorah!